is the marine and the aeronautical science, but also the environmental sustainability, the science and the information technology, of course, and the biological science. So there are a very big contamination between different fields. We say that we study from the star to the deep ocean because our interest is also in oceanography and climatology. So we brought a large different fields. So I don't want to speak about the different fields, but because there are a lot of fields of interest. But I want to stress the importance of this day because we merge our knowledge on the physical science, on the atmospheric science with the information technology. So welcome to this event and hope it will be very interesting for you. And we see you at the end of this day. Okay? Thank you very much and see you later. Don't need it. Thank you. Don't need to clap. Thank you. So the first speaker is the colleague Raffaele Montella, and introduces himself.
On? Check, a post. I'm Raffaele Montella. I'm associate professor in computer science at the University of Naples Parthenope, Department of Science and Technology, and I have two big interests, working interests, and I have a lot of interest. First of all, I like to do high-performance computing. That means using not the regular computation equipment, but what is on the edge between the possible and impossible to do new amazing things. The other great interest is environmental modeling, using this computing power to predict, for example, what will be the weather tomorrow. Here, it's nice because the weather is almost nice weather every time. But being here for the last 2 days, we learned some peculiar behavior of the environment that needs, even here, detailed weather forecast. For example, to predict when will be or not the fog, a really deep fog for flight, landing, and takeoff. So about weather forecast, we use the apps and usually say, okay, let's check the weather. And then, well, it's easy to check the weather because the weather is on the app. We have just to ask the app and the app answer. That's fine because the app does, quoting, sorry for the other hand, quoting, does the weather forecast that actually is not so easy. About computing power, well, I don't know if you are familiar with the classic Fiat 500, but the classic Fiat 500 is just a car. It's a really simple car. It's a car from 50s, for 60s, for 70s, but there is a date in the automotive sector that is 1999. It's a kind of a very important date because it's the time when actually any simple car is equipped with more computing power that was been used to send the man on the moon and back in 1969. That means if we drive a car that is newer than 1999, we are driving something that is very complex, that is a computing network on board, sensors, actuators, and whatever. And what about the computing power? And an iPhone 8 is an old one, is 2017, something like, I don't know if you are familiar with the Flintstones, but something of the Stone Age, and has more computing power than a Cray 2, a supercomputer of 1985. So the app is just the last step. We have a lot of work done by experts in atmospheric physics, experts in numerical mathematics, experts in high-performance computing, experts in engineering and networking to making all this possible. And finally, very expert people that can take some numbers that could be really ugly numbers in something nice as icons of sun and clouds. And finally, now we have a touch of magic using the artificial intelligence, because the app is just the peak of an iceberg of a huge computing power and, above all, human power behind, with a perfect mix between science and technology. And then the presentation. This presentation, the name, it came from supercomputers, where we are computer scientists, and so this is the focus. So weather forecast from the computer scientist point of view. That means we will talk about weather forecast and supercomputers, and the weather forecast of and artificial intelligence with Professor Angelo Ciaramella. And finally, we will talk about how to make a brand new weather app with Professor Michele Di Capo. This is the schedule of the presentation today, and this is my right now. Okay, don't look the time because you know the time is relative. So, how to do weather forecast? Weather forecasts are something really complex because the Earth system is complex, and to do the perfect forecast, we should know perfectly the state of the atmosphere. That means every square, or better cubic inch or centimeters of our atmosphere from the ground level to the troposphere, we should know exactly the state. That is basically impossible. We can mitigate this impossible, even because when science and technology mixes, the word impossible has a flag that is just pushed forward. And we can use observations. That means weather stations or, for example, weather radars or sensors connected to balloons, or the network of flights that during their routing, they collect data. The reason because the weather forecast in the last year are not perfect as before, probably is because we missed a lot of data from the airplanes and during the pandemic. The other source is remote sensing, of course, as a huge amount of data that could be collected, statistics, and time series analysis, and numerical models. I really hope my professor, Giorgio Budillon, don't look this slide, because this slide is made simple, something that is one of the most complex equations on the Earth. Believe me, the Navier-Stokes equations regulates everything on the Earth. The flow of your blood in your veins, or the weather forecast, or the flow of the wind on a high-performance sailing boat, or the behavior of the foils on a high-speed sporting car are all managed by the Navier-Stokes equations. And this is the most childish way to explain how the speed of an air mass is related with the pressure gradient, basically how the air pressure is varying on the surface, how is related with the Coriolis force that is related with the latitude, and we have not to forget the gravity acceleration. Here is g, and the A, this is frictions and other parametric stuff. Believe me, this is super simple, and I think Professor Budillon will be definitely not happy with me, but is the best way to explain everybody what is the problem. And this problem computationally is super complex. How the numerical weather forecast was born and when, it's incredible, it's in 1922. If you Google about Lewis Fry Richardson on the internet, you can find a paper dated 1922 where this guy describes perfectly a supercomputer, a parallel supercomputer, and a parallel program to solve the equation of the state of the Earth. But that's incredible, because this guy talked about computers, meaning that in that time the computers are just human performing calculation. And Richardson unfortunately failed because of a lack of computing power. He had no computing power. The first numerical weather prediction was in 1915 in USA, and there's the weather team that was a great scientist of the time, but the most interesting thing was who was heading the numerical mathematician team. Was John von Neumann. Okay. Okay.
Thank you.
who was explaining to us the complex mechanism that's behind weather forecast apps. So I'd like to thank, first of all, the University of Parthenope for bringing this innovative workshop here, and in particular, Professor Pascazio for organizing the session. And I'd like to leave the floor now to Professor Montella. Thank you.
Okay, back online. And just to recap, we are talking about how his complex producing a weather forecast, if we consider that a weather forecast now are available on a mobile app, so just pushing a button, we know the weather forecast. In the truth, there is something very complex from the physical point of view, complex from the computational point of view, and finally, even complex from the user interface and user experience point of view, because translating a weather forecast, numerical weather forecast from the numbers carried out from a numerical model or a numerical model enhanced by artificial intelligence is in sun and clouds is something that could be amazingly difficult. So the computational meteorology was born in 1922 when Louis Fry Richardson published a paper about how to do that. That's incredible because this paper is available on the internet, maybe on Wikipedia. And if you read the paper, you can read about computers that interact each other and exchange messages and have storage and whatever. It's 1922. Just computers is the word, the English word for people that manually make computation. And Richardson unfortunately failed in his experiment of producing numerical weather forecasts because a lack of computing power that now we have. We have a lot of computing power. And when the first numerical prediction worked was in USA in 1950, the interesting thing was, yes, of course, the weather team was top scientists of the time, but the most interesting thing was the other guy involved in the project is John von Neumann, is the father of a computer architecture. That means the two things, computer architectures, computer science, and weather forecast was something that walked the path together since half a century. And what is a supercomputer? A supercomputer is a computer that has top-level performance if compared with a computer that is on the shelf. Just trying to compare a desktop computer as a performance measured in hundreds of gigaflops till teraflops, while a supercomputer is 100 quadrillion of flops. That means 100 petaflops. How to make supercomputing on high-performance computing? For who is not familiar with this, a supercomputer is built, joined together more computing nodes. Each computing node in a modern supercomputer has more processor, each processor more cores, and all is connected with a high-performance network. Usually, this high-performance network could range from 1 gigabit to hundreds of gigabits. There are other components that are used, especially in weather forecast, but then we will show even other application, are the storage, of course, and today computing nodes can be powered by accelerators. Accelerators are, who is a video game lover knows these accelerators, because these accelerators are at the beginning were designed to accelerate graphic interaction for video games, but then someone noticed that using the same processors to perform math works and not just graphic works can be used, and then basically the top brand NVIDIA now is one of the two actors in this business. And the most part of today's supercomputers is accelerated by this kind of hardware. Just thinking that in our department we have 2 supercomputers that to be a medium large department is a lot. One supercomputer is completely dedicated to weather forecast for operation weather forecast, and the other one is dedicated to mainly to research in artificial intelligence. The new one, the one dedicated to artificial intelligence, has 81,000 processors, GPU processors. It's a huge amount of processors. Supercomputers' challenge to score better and better on top 500 is kind of computation that is 2 times per year, one in June and the other one in November. Especially the one in November is take alongside the supercomputer conference, and each year is awarded the most performing supercomputer. Actually, now the first score are the Chinese supercomputing. Supercomputers, the most part of supercomputers is Linux. That means open source software, and the most part of supercomputing is done with open source software. This is very good because supercomputers are hugely expensive. So if you want to start to learn how works supercomputing, doing something practical, doing that on the first-class supercomputer could be not super easy because it's complex to use, it's very regulated by rules and policies and whatever. Why? It's not too difficult to create a supercomputer connecting together off-the-shelf components. The applications are really diverse and different: quantum mechanics, climate research, and weather forecasting. The equations could be even similar, but the temporal scale is completely different. Oil and gas exploration, and I think here have some applications. Molecular modeling, vaccine and drugs. We developed a vaccine in a ridiculous amount of time. It's basically 1 year and a half, thanks to scientists interacting with the supercomputers. Cancer research, physics simulations for everything, especially high energy physics, and space, in the aerospace, and crypto analysis. As I told a few minutes ago, supercomputers are incredibly expensive. The top supercomputers cost about $10 billion. Coarse is something that is huge, is strategical, whatever. How to make a supercomputer to do, or to learn about supercomputing, or to do weather forecast. There are few alternatives now. One alternative is using high-performance cloud computing. Basically, public clouds, as Amazon Cloud, offer some on-demand supercomputing-like instances. And the other one is the most amazing. I like it because I did the first one in 1997. Is do it by yourself, Beowulf supercomputing. And you can do that. It's easy. You have just to buy off-the-shelf components, desktop computers, and connect together with a high-speed and dedicated network, and install Linux, and configure some software for message passing, basically how programs can send a piece of data from between one computing node and another node. And actually, if you are familiar with this, in a few hours, you have your mini supercomputer. Of course, you cannot compare the performance, but the behavior is almost the same. And you can use even Raspberry Pis. Raspberry Pis, okay, now there's the silicon crisis, so the Raspberry Pi is not super cheap, but with a bunch of Raspberry Pi, you can build a mini, small supercomputer, a nano supercomputer, but it's perfectly working. So we have a supercomputing, we have an operating system, it's free, it's open, it's Linux, and then we need a software that implements the weather model. That means is a software that completely provides the solver of the question of the state of the atmosphere. In our experience with several models, now in production, we have a model, an open source model called Weather Research and Forecasting Model. Is open source, is available on GitHub. If you are familiar with this model, you can set it up and running in less than 1 hour. If you are not familiar, it's a little tricky, but there are a lot of tutorials to do that. Unfortunately, we don't have enough time to do that, but it's pretty easy following the tutorials. Now, just you can update the checklist because we have a supercomputer, we have an operating system, we have a weather forecasting model. We are all set except what? Weather forecasting models resolve differential equations. To solve differential equation, we need initial conditions. To have initial conditions for a local high-resolution weather forecast, we need data from another forecasting model, a global model. In my experience, I use two models. One is the model provided by the European Center for Medium Range Weather and Forecast for France, ECMWF, and the other one is the Global Forecasting System from NOAA and ANSEP. For the production of our weather forecast, we use the American one because it's free. The European one is not easily available, publicly available for operational weather forecast, long story. So we use the other one. If you want to try to experiment the weather forecast on your computer and you are not crazy about the performance, means maybe you have to have the weather forecast of tomorrow. That means 24 hours, you have to wait for 3 days. That is useless, but you can do it using this data that is publicly available. As I told, to solve differential equation, we need to discretize the domain. Basically, the domain is a geographical matrix covering a part of the Earth on which we want have the weather forecast. And of course, we have not to forget that is three-dimensional because we have latitude, longitude, and of course, the age. Domains are characterized by a geographical center, coarse, and horizontal extensions in terms of kilometers, and a horizontal and vertical coarse. Resolution. That means the idea is exactly the same of a digital picture shot with the mobile phone. As much you have a megapixel, higher resolution, better pictures. And of course, we have a vertical resolution. For example, this could be a domain for the Mediterranean area. This is a domain that is 300 by 200 cells, and the resolution is 25 kilometers. That means this area is divided in pixels, just to use a common term, it should be cells, wide 25 kilometers by 25 kilometers. Is it useful, this kind of a resolution? Actually, not. That means, for example, if you have a mountain or a really slopy mountain, with this resolution, basically you have something that is flat because the height of the Earth is averaged on 25 by 25 kilometers. So it could be not so much useful. This is exactly almost the same domain on the Gulf area. I found really fascinating testing the model on the Gulf area because it was new for me. And even in this case, we have almost the same resolution. We have the same resolution with almost the same dimension. Why it is not so much useful? Because in a perfect world, we say, okay, 25 kilometers by 25 kilometers could be not so a nice resolution. we can improve the resolution just increasing the density of the cells on the heart. Yes, but doing that, we need, first of all, better data. That we have that better data because we have the technology to acquire and process better data. But we need more computing power. And this could be not effective because computer power could be not infinite, could act as infinite if you use cloud computing, but if you want to do operational forecast, the one that finally arrives on your app, you need to use at the best the computer power you have. So there is a trick. Basically, if we nest one domain in another domain, maintaining basically the same amount of cells, but at high resolution with a rate usually or 1 to 3 or 1 to 5, we can increase locally the resolution of the model using, yes, more computing power because it's like we have to run 2 times the model, but we save computing time if compared with using high resolution with all the main domain. Of course, my dream is a resolution of 1 kilometer on all Europe, for example, but for now, I don't have this computing power. So what is the trick? This is the trick. This is the actual setup in the Weather Forecast Center at the University of Naples Parthenope. We have 3 computing domains. One is the Mediterranean area, one is on the Italy, and the other one is south of Italy. The resolution of each domain is 25 kilometers, the coarse one. Then we have an intermediate of 5 kilometers, and then finally one of a local of 1 kilometer. And this is exactly the same setup in the Gulf area. What is the advantage of this? In this case, when we produce highest resolution weather forecast, we not only increase the final results, so we have a better pictures. No, definitely not. We have a better description of the orography, of how the mountains and the coasts are modeled, even about the land use, because in the weather forecast it's crucial having a correct and exact land use, because the interaction with the sunlight and the land use change the modeling. And this is the Center for Marine and Atmosphere Monitoring and Modeling and Application is the Weather Center of the University of Naples Parthenope. We have a mission: deliver the best possible environmental operational forecast, not only for weather, even for ocean, for pollution, and whatever. This is a workflow. Workflow is a complex set of models that interact each other in order to provide simulations and forecasts involving different components of the Earth system. For example, in our setup, we have the weather research and forecasting model that produces weather forecast that is used by final users with our app, but even to drive other models. Other models, the correct technical term is, are offline coupled each other. In this way, for example, the weather forecast model drive the model that forecast and simulate and forecast the sea wave models produced by the wind. Or at the same time, the ocean model that simulate and forecast the behavior of the sea currents along the coast. And why are so high resolution? Because we produce other modeling and other for specific application. For example, we have a model that we built completely ourselves and is, of course, open source, so available to everybody, that is used to model and predict the pollutants, how the pollutants are transported in the seawater. And now there is the little nice addiction. What is ingrained in this workflow is what the artificial intelligence is adding to our system, because what I show you till now is a really classical approach. It's advanced as you wish, but it's classical approach in environmental modeling with supercomputing to implement models that are designed by field experts, are checked and verified by field experts, and then we run operational forecasts. But now we want to do more, because really often we don't have the math connecting two phenomena, or the math is too much complex, or the math is not already is not already ready to be a software. In this way, in all these cases, the artificial intelligence is the best to provide a new kind of predictions. For example, we can use in artificial intelligence for local extreme, not intense event, to recognize pattern. For example, in the Mediterranean, we have the Medicane, the Mediterranean hurricane, that now are dangerous for the man activity and the sea on the coast. So predicting and tracing the trajectory is crucial. And then we use artificial intelligence to predict contamination in mussels. Those are some products of our systems. This, for example, the products of the ocean model connected with the weather model. And these are some outputs of the artificial intelligence-based applications for example, for lighting prediction or weather pattern extraction. But all those outputs are freely available as open data in diverse and different ways, are available as opened up server that means that could be automatically read by Python or MATLAB or whatever, or using the world map server as GIS components. But this is the most interesting, even because you will explore this future. These data are available as open web API for our applications, but even for the application of the next generation of creatives that will be eager to create what we have not already designed. For example, this is how our data are exposed. In the practical section, you will do that hands-on. Here I can just show the methodology. Basically, the web API are available with a nice interface in the way even the humans can test and understand the actual data. For example, in the here, I ask a time series about the weather forecast from now, since the next 168 hours, using the weather forecast. The code of the weather forecast model is WRF 5. The strange code is the code of Naples, of the city of Naples. And then just clicking on execute, I have this. Okay, now we are back on our app or weather forecast. This is what the app receives. And then it's on the app creators find the best way to have the best user experience to transform these numbers in information for humans. This is a JSON file this JSON file will be in your playground for the practical section. And what the meaning of this data? First of all, there is another API that you can ask about what each data means, because metadata really often are better than data. But here, for example, CLF is cloud fraction. Unfortunately, for people in Napoli that now are connected with us, and fortunately for us, the cloud cover in Napoli is about 99%. Believe me, maybe you cannot understand here 99%, but, and in Napoli is raining since days. Then we have other, actually this is the screenshot related to a few hours ago when I took this. It's not run real time. We have, for example, RH2 is the relative humidity at 2 meters, is in percent. That means 80% of humidity. T2C is the temperature in Celsius degrees as 2 meters. It's 9 degrees. Okay. And there are some other data. What you see with the U8050, for example, are data that are really useful for professional oceanographers, because it's the profile of data on the atmosphere, along the atmosphere. Then other data that could be easily used in your application is, for example, the wind direction. Winds, E is for east, or the wind speed at 10 meters is in meters per second, 2.9. And then finally, I conclude with the pictures from our application. And I'm very happy that you will be here testing our system and our methodology. Now, the next speaker will introduce how the artificial intelligence is changing this field. I don't know if I have a question and answer break, or if this is, yeah. If you have a question, I'm really happy to answer. I really do love what I do, so I could speak for hours. So believe me, yeah, you can stop me. If you have a question, I really, and if you have a question and you don't do question now, you can do question after. I will be around. Oh, yes, sorry, please.
Most of the forecasts are done for the ocean surface?
Actually, not only. Actually, is very the interface between the ocean and the coast is very important for mankind, because basically the most part of human activities are there. We are people from the coast, because we live in the middle of the Mediterranean Sea, and we are there. You live here, and so we really need to know the weather in a really detailed way, because this changed the activities. For example, think here about the tourism and all the related activity. Let's say here we want to organize a top-class regatta. Let's say America's Cup. And we need to know exactly at what time the wind will rise, at what speed, and in which direction. I was the responsible of a weather forecast for the Universiade in Napoli in 2019. And in particular, I had in charge the weather forecasting for the sailing races. And the sailing committee asked me at what time and how, and if 200 degrees, the wind from 200 degrees or 25.
So my question is more technical than that. So for this specific intertidal area,
yeah.
how do you make the model seamless?
Oh, okay, yeah. there are two ways to do that. We do it in the simple way that is good for operational, but is not good for science. For science, the way is another one. We use the offline coupling. That means we transfer the drug from the lower end of the atmosphere to the ocean, using basically some parameterized, we use U star to transfer this. That it works for operational. For science, the approach is different, because for science, instead of using two different models, you can use one single model or the two different models, not offline coupled, but online coupled. That means when the solver arrives on the interface, another thin layer of software couples the equations, not the results, between the sea and the atmosphere. The results are better, of course, if it is better simulator. For example, for us, if there is a transfer flux of head between the sea and the atmosphere, we don't have the effect on the atmosphere with our setup. That is for production. If we have to do this for science, we can set, of course. Vice versa, the head between the atmosphere and the sea is transferred. So it depends by what is your final target. We have a clock problem, because we have to produce the forecast before the forecast have to be forecast, otherwise simulation. But for example, we have on the other supercomputer, not the one dedicated for weather forecast, we have some scientists that are oceanographers / meteorologists. They run exactly the same models, but configured in a different way, and they do magic things. Of course, they don't care about the timing. They don't care about the clock, because it's not their interest. They love the science in this, even because their results then will be transformed in parameters for our results. You're welcome. Sorry, when I start, I don't stop, so please. Okay, may I introduce you? No? But I'm honored to do that.
No.
Okay. Okay, next speaker? Yeah?
Okay.
Yep.
I think that it's better to stay there.
Yeah, okay. Okay, next speaker is Professor Angelo Ciaramella. He's a super expert of artificial intelligence. And I'm very happy to share my project with you.
No. Okay. Okay. Good afternoon. I am Angelo Ciaramella, and I come from the University of Parthenope, and in particular from the Department of Science and Technology. And together with Raffaele and some other researchers, we are working on weather forecasts, and in particular, I am a little bit expert on artificial intelligence, and then I am just adding to these talks the part of artificial intelligence. And in particular, we have seen the high performance computing part. We will see something about the artificial intelligence part, and we will see how we can implement some simple apps on a computer. But in particular, I am the director of the iOS Foundation, Apple Foundation of the Parthenope, and Michele Di Capua will introduce you to some things on Swift. Then, just to start, we have seen that we need for manage
some kinds of data about the weather, we need of some supercomputers, high-performance computers, and so on. But we can start, and we can say that some of the algorithms that are used for forecasts are based on numerical weather prediction, and in particular are mathematical models for accomplish this task. In the last years, and in particular the last months, we have seen that there are a lot of works on the use of the artificial intelligence-based models. In particular, now we know the deep neural networks and the deep learning, and that are applied for prediction of in the field of the meteorology. In particular, for example, there is a work of DeepMinds that predicts almost exactly where it's going to rain in a few hours. And for this is an example. Just I have the point. Yeah. This is, for example, a target. We have some models based on a particular type of deep neural networks that are generative adversarial neural networks, and that are used for forecasting in 2 hours and to predict the weather. And for example, this is the comparison with respect to other models like UNet, that is also another deep neural network model. In particular, for example, in this example, a deep generative model is used. In particular, we start from some known models and data, and then we forecast, and we are able to predict the weather with I think 19% of accuracy. But we can also ask that this is a good problem, but there is another problem. This is interesting, and this is the prediction of the pattern of the hurricanes. In particular, there are also other works on this. This is an example of the damage in Louisiana of the Hurricane Z, and in USA. And for example, to approach this prediction and the path prediction, deep learning approach can be used, and in particular can be used in this case an LSTM, that is a particular type of recurrent neural network that can predict the weather and in particular the path of the hurricane. This is based on this particular kind of deep neural network, but to approach to this prediction, we need of a great database of information. In particular, there is a database of tropical storm tracks since 1979, and these are a huge database. Then we need some information about, and then we need to manage this data, and in particular we need to manage this big data, and from a point of view, but we need also high performance computing for learning, for the models. And then in our department we have some experience on big data, on high performance computing, theoretical from the point of view of the weather, meteorology, and some other things. Then in this, for example, case, we can have data from grids of global atmospheric parameters, and from these parameters, then we obtain the database. The database is used, for example, for general architecture that is based on convolutional neural networks, and for example also for techniques like in the first example, the LSTM, that is a recurrent neural network. Then I want to just focus on some basic concept of these models, because for us, for some of you, could be interesting to understand how we can approach this data. And then now I would like to explain the artificial intelligence from a different point of view, and why we need to approach with deep neural networks instead of the numerical models. In particular, in our case, we have seen that there are a lot of works from Google also for forecasting and for predict of the path of hurricanes, but we are focusing on a particular problem. The particular problem is the medicanes. Medicanes are the Mediterranean storms that we are observing in these last years. In particular, last month we had a medicane, two medicanes in the Mediterranean area, and the global simulation is difficult in this case, because we need local information, and then we are starting from this point of view. Then we are acquiring information. We are using high performance computing from the simulation of and after we are using artificial intelligence for predict these medicanes. In particular, we can start just to understand what are we doing. We can say, and we can start from the idea of artificial intelligence. We have seen the HPC, and now the artificial intelligence is the approach and the algorithms that I'm to develop intelligent mechanisms. And we can divide this world in two main theories that are hard artificial intelligence and weak artificial intelligence. hard artificial intelligence is the mechanism that can be smart, and the machine can be smart, but we are focusing on weak artificial intelligence, where we have a behavior of the machine that can be like intelligent. We can say that the artificial intelligence from the first point of view can start from a basic concept that the human mind is like a program, and the brain is the hardware of our brain. The brain is the hardware of our thinking and the reasoning and so on. Then the idea is that we, from the human mind, we have some inputs, and from the input we have some outputs, and the brain is the parallel hardware that elaborates this data. We now, today, we speak a lot about deep learning, but deep learning is just a subset of the artificial intelligence. The subset of, because we have also a particular thing that in artificial intelligence we have also, we will see something, computational intelligence, some logics. We have also other approaches, and in particular, one of these is the deep learning. But the deep learning is the main step to arrive to the representation learning. The representation learning can be used for extracting information from data autonomously. And then we will see that the machine learning is just a little part of the world of artificial intelligence. In particular, we can see that machine learning is based on support vector machine, for example, so Bayes nets, or some statistical learning, pack learning, and so on. But there is all the part of computational intelligence, that the part that we today use, where we can consider neural networks, and we can divide two parts and two kinds of neural networks, like shell of neural networks, in particular neural network with just like a hidden layer that can be an universal approximator, and then we can classify, and we can make a regression of all the functions, and then it's enough. But we ask, and we have seen that going in deep is better than have the shell of neural network. And then we see also why. But in the computational intelligence, and is really used, is the fuzzy logic, that is one kind of artificial intelligence mechanism that is in this last year is really used because one kind of fuzzy logic is the introduction of the reasoning in the neural network stuff. For example, for the neurofuzzy models, but there is also another thing that I want to focus, but is the explainability of the models. We will see that the deep neural network is very well, is good for classification, but we need some interpretation of the model, and we have the explainable information about the neurons in the neural network. Then also we have other approaches based, for example, on evolutive approaches like genetic algorithms and colony and small optimization and so on. Then machine learning is just a little part of all the world of artificial intelligence. For example, this is a support vector machine that is based simple on the transformation from an input space to a feature space using some transformations, in some sense the kernels, and using particular kernels and functions, and then it's based on this transformation and the using of the cat or the simple neuron for divided regions. This is the aim of the support vector machine. The neural networks, it is the first step to have together some information, some different kind of cats for classification, and then for this reason, multi-layer perception, we can say that multi-layer perception with just one hidden layer and sigmoidal functions, and this theorem of Bishop, can approximate any continuous function. And then we can obtain any classification using just one hidden layer. Then we have seen also with experiments that adding some other layers, we can arrive to deep neural networks. Deep neural networks where we have some hidden layers. Adding hidden layers, we have seen also experimentally that we can have the representation learning. Then we can extract automatically information from the data that are the information that we need for classification. Then there are also the other models that we have seen, in particular a logic in artificial intelligence, and one logic is the fuzzy logic. But this is a word. And the idea of fuzzy logic, sorry for Italian language, the idea of fuzzy logic is to represent information using the membership functions. Then, for example, temperature, we can consider temperatures like low, medium, high. From this, we can make a decision support system very simple, using simple rules like if then else rule. And then there are some, for example, models. These models are based on fuzzy inference. For example, if the temperature is medium and the other parameters is high, then we have some consequence, and then we can make decision. And then is properly from the approximate reasoning of the human. The genetic algorithms are based instead on the our idea of the evolution of the world, and in particular, in this case, we use chromosomes for to make this evolution of the systems, and to arrive to an optimization. And we can demonstrate, for example, that genetic algorithm can obtain a global optimization instead of the other approaches also based on deep neural network that can achieve a local optimization. Then, for example, for multi-objective optimization, it's better to use genetic algorithms instead of with respect to deep neural network, because we can achieve a global optimization instead of the local optimization, because we know that for example, for the case of neural networks, the main point is where we start to optimize, in particular the weights that we use in the first step. In the case of genetic algorithms, we can explore all the world, and then we obtain the global optimization of the function. The last, that just to say how we can approach to optimization, and in particular, for example, for path search, another algorithm can be the ant-colony optimization, that is based on the idea of the search of the paths of the ants. And then this an algorithm, for example, used for Salzman problem and some other optimization approaches. Then, but we now, and then in our works, we focused on the deep neural network, and in particular some kinds also of artificial intelligence approaches. And we can say that the idea of the neural network started in 1940. There was a famous work of Mellock and Pitts that started with the idea of the neuron. From that, we had the perceptron after the other works, arriving to our idea now of the representation learning that introduced the deep neural network. In particular, we can consider two main steps. Until the deep neural networks, the main idea was the approaches of machine learning, where we could extract information from data. And then, for example, extract information, we need also the transformation of this, the base of the data. And then we could use on this data, for example, support vector machine, neural network with just one hidden layer. We can use bias nets and other machine learning approaches. But this the problem is how we can approach to the data representation. In the deep neural network, we have automatically the representation learning. Why? Because in the deep, we can extract the information automatically without to use particular information. An example is this. For example, if I have a signal, for example, the audio, the idea of a classification of some different speech different voice can be, for example, male, a female voice, then can be in this sense. I can extract information from the audio signal, and then we can classify. But using deep learning, automatically I can extract information from the data for making the classification. Two things to say. One for me is that in this representation learning, the deep learning is like a series of fear filters, finite input response filters, because we can say the convolution of the convolution neural networks like different filters in deep. And then the idea is that to extract different information for each level. This is the same for the images. The idea is that we can extract information using filters in deep automatically without consider the fixed filters, but learned from the data. And then this the idea of the representation learning. Then automatically we filter information from the data automatically without to fix the weights. Then, but the idea of the explainable artificial intelligence is that, well, I make these steps. How? Why? Are there enough for classification when, for example, in clinical solution, I have to make a decision? Then the idea now is to apply some approaches to interpret the information in the neural network. Then, just to say the idea is if we have to classify, for example, an image, the idea is that to extract in deep this information is they are like filters in deep. The hidden layers extract the information that can be used for classify from car, person, and animals, for example. Okay, just I want to jump this because there are some things that I have just said, but I would like to focus just on this, that in these last years, things, I think, and thanks to the high performance computing too, we have that the data set are growing from the data. For example, starting from the iris, 150 sequence, that is very small. We arrive to the last, for example, ImageNet and so on, that are huge data sets. And thanks to high performance computing, we can make fast, not so fast, but some elaborations that with these data sets, and then we can have also the growing of the connections in the neural networks and in the deep neural networks. For example, in the ResNet, we arrived to 100 hidden layers. That is a huge number of hidden layers, but we have also the growing of neurons in the neural networks, and then we can represent information with more details, and then we can classify the information with more details. For example, if we consider the ImageNet dataset, we finish in 2015, but we arrived also with an error rate that of classification of ImageNet that is near zero, more or less. For the person that are interested in artificial intelligence knows that zero is impossible, but it's not is overfitting for the data. But then we are making classification very good. Okay, about our works on medications, we are considering and we are focusing on Mediterranean subtropical hurricane storms, and we developed a workflow that we have seen in the first part, the acquisition and the prediction of the weather, and then we introduced the storm seeker. Storm seekers is use artificial-based approach to recognize, classify, and the prediction of the medications. We have seen part of this workflow. We had the workflow of on the right. That is the workflow where we have the part of the artificial intelligence part, where we had, for example, an unsupervised approach for making after the classification with the unsupervised approach. In particular, we use in the first part in an autoencoder and clustering approach that is negentropy based clustering, and in the second part we use a deep learning approach based on multi-layer perceptron. This is just full connect model. For this is called multi-layer perceptron. Okay, these are the parameters, for example, are temperature, sea level, pressure, wind, and some other. From this we make feature selection using some approaches for feature selection, and we arrive about 10 parameters, okay. 10 parameters, and then we apply this hierarchical clustering that is called negentropy-based clustering that we have studied in for also other fields like bioinformatics and so on. Then the idea of this approach is that instead of using a distance like Euclidean distance, we use negentropy information for making together the Fisher directions, the agglomeration of the clusters with the same distributions. And then, for example, we can demonstrate that with this approach, we can have the classical clustering of the information, like in the distribution that we have seen here. Then we apply this on particular kinds of storm. That is a storm event during the period of October in 2018. Then these storms collapse, make the log collapse of the breakwater of the Marina Terrapallo in Liguria. And then using the clustering, we obtain, for example, the recognition of this part where we can consider and then are labeled by a specialist in this case, that is Vincenzo Capozzi of our department, and then after this we applied the classification, and then in the simple in this simple data set we can demonstrate that we have a good performance, high performance, using the classical cross-validation mechanism, and then we can obtain these classification results. Okay, I think that I can stop also here, but I just would like to conclude that we are focusing in these works, in our works of our department, on particular type of storms that are medications, and in particular we are now focusing on using also other parameters for predict these storms, and I think that that's all. If you have some questions, okay, I am free. Yes, any question? Please, please, please. Yeah. Okay, we tried some approaches. One is based on one approach that we introduced that use the sparse coding, and like in some sense, sorry, lapsus. Okay, sparse coding. I don't remember the name, just for this moment, I think. Okay, it's based on sparse coding using also the hierarchical selection of the features. We compared also with other, for example, using boosting, where we select and rank the features that are more usable for classification. And then we compared, and we selected these approaches based on sparse coding. If you want, I can give you the exact. Also, there is a GitHub with the software that you can download. Okay. 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 Just 1 hour. No, okay. You know. You know.
Welcome, everyone. I think it's better to take a break now, and after I will introduce you the iOS Foundation program that we have in collaboration with Apple International, and we will start the hands-on lab activity. I think we prefer to just have a break now, so after we can start, more fresh. Okay? So enjoy your lunch. See you in 45 minutes or half an hour. 35 minutes. We'll start with the second part of the workshop. Thank you.